Dear students, in coming section we are going to learn one more application of first law of thermodynamics, that is finding efficiency of a cyclic process. For this purpose we are going to select few illustrations, and through coming illustration we will learn this concept. So let us move to illustration number 1. Illustration number 1 is about an ideal monoatomic gas which is used to operate an engine, and this is the PV diagram, that is the cyclic process of PV diagram, and we need to calculate efficiency of this cycle. Okay. So let us first discuss what is the meaning of efficiency. Efficiency means output divided by input. Output we always get in the form of work done, that is the work done by the engine or work done by the cyclic process, and input is always expressed in the form of heat absorbed by the engine or heat absorbed by the cyclic process. That means in mathematical form we can write efficiency as W total divided by Q in. Q in means positive value of Q, right. In this efficiency formula we have W total divided by Q in. So let us first calculate W total. Calculating W total is easy in this PV diagram, because we know in PV diagram, in cyclic process of PV diagram, work done equal to the area enclosed by the PV diagram, and area enclosed is this much. That means if we able to calculate this area, we can find the W total. We know this is the clockwise cyclic process, or clockwise cyclic process always have the positive work done. That means work done will be positive, and we know this coordinate is P naught, that is 2 P naught minus P naught equal to P naught, and this coordinate is 2 V naught minus V naught equal to V naught. That means the work done equal to total area, and this area equal to P naught multiplied by V naught. Okay. So we calculated the W total value. Let us take this temperature, the temperature of point 1 as T naught, right. That is T1 equal to T naught. We can calculate the value of T naught by using the ideal gas equation also. Okay. We are going to take this process, that is a process number 1 to 2. This process is isochoric process, because we know volume is constant in this process. So this is isochoric process, and in isochoric process individually if we say work done will be 0, that means while moving from 1 to 2 there will not be any work done. Now let us analyze whether in this process heat is absorbed or heat is rejected, right. And we know this is an isochoric process, and we can write this equation PV equal to nRT. This V is constant, that is P is proportional to T in this process, and if pressure is double, temperature will also double. That means temperature at position 2 will be equal to 2 T naught, right. We know W12 equal to 0 and temperature at point 2 equal to 2 T naught. That means temperature is increasing while moving from 1 to 2, and this is the isochoric process, and in isochoric process we can write the heat received by the system as NCV delta T. Delta T means final temperature minus initial temperature, that is T2 minus T1, and T2 minus T1 is a positive value. That means Q12 will be positive, that means heat is absorbed by the system. That means Q value will be positive. Let us calculate this value. You know this is a monoatomic gas, right, and for the monoatomic gas we know the value of CV equal to 3 by 2 R. So N multiplied by 3 by 2 R, and multiplication 2 T naught minus T naught, and this is equal to 3 by 2 N R T naught, and we know N R T naught is nothing but from ideal gas equation, this is equal to P naught V naught. So this value is 3 by 2 P naught V naught. That is the work done, that is the heat absorbed by the process 1 2. This is a positive, that is a Q in. Okay. Now let us move to process 2 to 3. Process 2 to 3 is isobaric process, right, and in this isobaric process we know From ideal gas equation, P is constant. If P is constant, that means V is proportional to T, right? We can write V is proportional to T. That means if volume doubles, temperature will also double. And here temperature is, we have calculated as 2 T naught. That means temperature at position 3 is equal to 4 T naught. Now, in this process, we can calculate heat absorbed or heat taken by the system. This is isobaric process. Here we can write W23 is equal to NCP delta T. Delta T means final temperature, that is T3 minus T2, and this is equal to T3 is equal to 4 T naught and T2 equal to 2 T naught. That means this value is going to be positive. That means heat is absorbed by the system, that is Q in for this process is positive, right? And value of Cp for this monoatomic, this is equal to 5 by 2 R. So, let us substitute this value. Now, after calculating, we can get this value as, this is 2 T naught, this is 5 by 2 multiplication. So, this is equal to 5 nR T naught, and we know nR T naught equal to P naught V naught. That means this is equal to 5 P naught V naught. Okay. So, we have calculated W23. Let us move to next process, that is process from 3 to 4. 3 to 4 process is a isochoric process. We know individually work done in this isochoric process is 0 because volume change is equal to 0. So, if we consider process 3 to 4, and from ideal gas equation we know V is constant, P is proportional to T, right? That means if pressure become half, the temperature will also become half, and here temperature we know this is 4 T naught. That means temperature will be half of this value, that means equal to T3 divided by 2, and T3 is 4 T naught. That means temperature at position 4 equal to 2 T naught, right? Now, let us calculate the heat associated with this process. We know this is isochoric process, and for this isochoric process we can write NCV delta T, and we know delta T for this process is negative. That means Q34 will be negative, right? That means heat will be rejected by the system here. So, this will be equal to N multiplied by 3 by 2 R multiplication 2 T naught minus 4 T naught, and this is equal to minus 3 N R T naught, right? This will be minus 3 N R T naught, and N R T naught equal to P naught V naught. So, this value is going to be minus 3 P naught V naught. So, we have analyzed 3-4 process. Now, last process is 4 to 1, okay, and we can observe here from 4 to 1, we need not to calculate work done because we have calculated overall work done here, that is the area under the curve. And here let us analyze whether heat will be absorbed or released. You can observe here in this process 2 to 3, it is from left to right, and here heat is absorbed, and this process from right to left, that means opposite to this process, that means heat will be rejected by this system, right? So, we need not to find this value, that is a Q41 we need not to calculate because it will be negative, right? So, in this process now we are not calculating the Q41, and now efficiency we can again write the formula W total divided by Q in. So, here we can substitute this value P naught V naught, and Q in is the summation of the energy absorbed in this process and this process, this one, right? And we are expressing this efficiency in the form of percentage. That is why we have multiplied this ratio with 100, right? And after solving, this value is equal to 200 divided by 13%. So, this is the efficiency of the cyclic process. Now, let us move to next illustration. In this illustration, a fixed mass of oxygen, that is diatomic gas, it performs a cyclic process ABCA, but it is in PT coordinate. and here we need to calculate efficiency of the process. We know efficiency is the output divided by input. Output is always in the form of work done by the cyclic process and input in the form of heat absorbed, that is Q positive. That means efficiency we can write W divided by Q in, right. This is the efficiency. Okay. Let us move one by one. Let us analyze the process first, A to B. We can observe this is the straight line, constant slope and passing through the origin. That means mathematically we can write this equation as y equal to mx, right, and m is constant, that is y is proportional to x. On the y axis we have p, on the x axis we have t, that is p proportional to t. And we have the ideal gas equation, we can write PV equal to nRT, right. Here we can write P equal to nR divided by V multiplication T. That means if V is constant, here also P proportional to T. That means we will have the same line if V is constant, and if V is constant, the process called the isochoric process. That means this process, that is A to B process, is the isochoric process, and in isochoric process we know work done equal to 0. That means we need not to calculate work done in this process. And here we cannot calculate work done by area under the curve. Why? Because it is not the PV diagram, it is PT diagram. That is why we need to calculate work done one by one. So, in this process we need not to calculate work done. Now, let us analyze whether heat is rejected or absorbed in this process. And we have proved this is the isochoric process, and in the isochoric process heat given to the system can be defined by the formula N CV delta T, right. And here we know this is a isochoric process, that means P is proportional to T. That means as pressure become 3 times, temperature will also become 3 times. If temperature at this point is TA, that means temperature at this position should be equal to 3 TA, right. And we know from A to B temperature is increasing, and Q is defined as N CV delta T, and CV is a positive value, N is also the positive value, and delta T is a positive. That means the heat is absorbed, Q value is positive, that means heat is absorbed in this process. That means there will be Q in. So, we can write QAB equal to N CV delta T, right. And this after calculation will have this value, 2 and 2 will get cancelled. This is equal to 5 nRTA, right. We know the heat will be absorbed in this process, that is Q in here. This is the positive value, right. Now, let us move to process B to C. From B to C we can observe here temperature is constant, and if temperature is constant, that means this is isothermal process, and in isothermal process we have the direct formula for calculating work done, and we have the first law of thermodynamics as Q equal to delta U plus W. And isothermal process, this temperature is not changing, that means this value is 0, that means Q equal to W. That means if we calculate W, we can find the value Q directly. So, let us write the formula for the isothermal process. This will be equal to N, that is the number of the moles, multiplication R, multiplication temperature of this process, that is equal to 3 TA multiplication natural log final volume divided by initial volume, right. But here we are given pressure, and we know in isothermal process P is inversely proportional to V. That means in the natural log we can write initial pressure divided by final pressure. This formula can be used, right. Now, we can substitute the value, right. If P and P will get cancelled, this is equal to 3 nR TA natural log 3, and this is also the value of QBC. That means this value is again positive. That means in the two processes, in this process heat is taken by the system or taken by the cycle, and here also Q is positive. This is positive, this is also positive. Okay. Now let us move to the last process, C2A. C2A is the isobaric process and temperature is decreasing because temperature here is 3 TA and temperature is TA here, right, and here Q equal to NCP delta T, and delta T is negative here. If it is negative, Q is negative, that means in this process heat is not absorbed by the cycle. But we need to calculate Worden, and for Worden this is the isobaric process. We can write here P multiplied by delta V. Delta V means final volume minus initial volume, right, and we know PVA can be written as nRTA and PVC can be written as nRTC, and TC is equal to 3 TA. So we can write this value, and after solving this will be minus 2 nRTA, right. So we got the Worden in each and every process and value of Q where it is absorbed or where it is positive value for the cyclic process. Okay. So efficiency formula W divided by Q in. So W we can add for each process and Q positive we can also add. So we can write this expression as this one, right, after substituting the value of W and Q in, and after further solving we can find this as 3 natural log 3 minus 2 divided by 5 plus 3 natural log 3 multiplication 100%. This is the efficiency of the cyclic process.